Hello everyone, welcome back. This is Mr. Hussein Mosapi. Alright, so in this video we'll be looking at a quick summary of kinetics and integrated rate laws. Now before we begin, don't forget to like and subscribe to the channel. Alright, now one thing you should understand is this. You will only encounter 0, 0, first and second order situations, that is in exam questions. So let's be mindful about this. So let's look at the summary. So when it comes to kinetics, we'll have these scenarios that you have to bear in mind, but I'll explain quickly how you get to understand these things. Now, just a quick reminder, K represents the rate constant, T represents the time, and whenever you see T to half, is simply just a half-life. So half-life will be explained later on. But now, looking at the summary table, we're having a zero order, and in this column, we're having a rate law expression, the integrated rate law, the linearized integrated rate law, the graph, then just a memorization tip, and the half-life equation. Okay, so for a zero order, be mindful that the rate is equal to K concentration A to what? To the 0. Then the integrated rate law is that the concentration of A at some time minus the concentration of its initial should equal to minus K at T. Then the linearized form is where you have the concentration of the reactant after some time being equal to negative KT plus the concentration of the initial reactant. Alright, so this is equivalent to one having y being equal to mx plus what? B. The graph, as you can see, has the concentration of the reactant in the y and the time in the x. Now, if you look at the memorization, which is C, C just shows that the graph should always be the concentration versus time. The half-life is the initial concentration of the reactant divided by 2 times the rate constant. If you look at the first order reaction, you're having the rate being equal to the rate constant times the concentration of the reactant raised to the power of 1. Then you have the integrated rate law saying ln to the concentration of the reactant after some time minus ln with the initial concentration of the reactant being equal to negative k watt t. The linearized integrated rate law states that ln of the concentration of the reactant is equivalent to minus Kt plus the ln of the initial concentration of the reactant. This is given by y being equal to mx plus b, of which the minus Kt represents the mx, the b is represented by ln, initial concentration of the reactant, and y is simply ln, the concentration of the reactant after some time. Then you have the graph, which has ln, concentration of the reactant after some time, versus the time. Now here the slope is negative. So here, if you look at the memorized tip, it's simply just L. So L just shows you that it's ln of the concentration versus the time. Then the half-life of a first order is simply equivalent to 0.693 divided by the rate constant. We don't really have the initial concentration in the formula, so don't forget this simple formula. Then lastly, we have the second order. For the second order, you have the rate being equal to the rate constant times the concentration of the reactant after some time raised to the power of 2. Then the integrated rate law is 1 over the concentration of the reactant after some time minus 1 over the initial concentration of the reactant being equal to what? Kt. The linearized integrated rate law is going to be the reciprocal of the concentration of A after some time, which is equivalent to 1 over the concentration of A being equal to Kt plus 1 over the initial concentration of the reactant, which is equivalent to y is equal to mx plus b. Then the graph is given in this format. So if you look at the slope, it's positive. So the half-life will be given as 1 over the rate constant times the initial concentration of the reactant. So among the 3 orders, it's only the second order which has a positive slope. But for the first, and the zero order, the slope is what? Negative. Then one thing you should understand is this. For a first order, in the y-axis, you have ln of the concentration of the reactant after some time. While in zero order, in the y-axis, you just have the concentration of the reactant after a given period of time. Now, one thing you should understand is that when it comes to graphing integrated rate laws, you should be familiar with the CLR. Now, C represents the concentration versus time, L represents the ln of the concentration versus time, and R represents the reciprocal of the concentration versus what? Time. Now, this is just simple, let me say a simple illustration explaining a summary of what we are looking at, which is kinetics and integrated rate laws. So now let's look at some examples, or let's say the types of questions that they'll bring. So I'll look at some basic questions so that we clearly understand. Let's begin with graphical questions. Now, the first type you have is where you analyze a graph. So analyzing graphs. So what you have to be mindful is this: you have to be prepared to deal with graphs in one of the following ways. The first way is choosing between different graphs to determine the order. So because sometimes they'll give you a table of which you have to plot all the values that you have, and by choosing between the different graphs you have, you end up knowing the order of the particular reaction. The second way is where you have been given the order. Okay, they'll give you the order, and you have to indicate what the axis must be. Okay, you have to label the particular axis. Then the last method, or the last way in which they can give you, is where they will give you the order of the reaction and they'll ask you to sketch the graph, of which this one is quite simple because we have the summarized table. So now these are the tips. You always have to use the clues given on the axis of the straight lines, or clues of the graph itself. Okay, remember we have positive or negative slopes. So figure out the order of the reaction with the same pattern by knowing which one is positive or negative. Then when given different graphs with different y-axis, the one with the straightest line represents the appropriate relationship that you want. So look at the y-axis and remember the CLR. Now the rate constant K is always positive, and it's positive because if you look at mathematics, we can consider it to be the absolute value of the slope of the straight line. So the units are based on the order and the specific time unit described. So be mindful that despite the slope being negative, the value of the rate constant should always be positive. That negative or positive in the slope just shows you the order of the reaction. Let's look at the examples. Now, for the practice questions, it says, for each of the graphs below, determine the order and write the corresponding rate law expression and the units of what? K. So we'll start with the first one that we have. So we're having a graph that shows the concentration of hydrogen peroxide versus time. So this is ln, concentration of the reactant, being H2O2 versus time. So we'll start with the first portion A, which is determining the order. Now if you look at this is ln. So ln of the concentration of the reactant versus time is simply the first order, if you can recall from the summarized table. Then they're saying write the corresponding rate law expression. So the rate law expression from the table, like we had, is going to be ln, concentration of the reactant, which is H2O2, minus ln, concentration of H2O2 not being equal to minus Kt. This implies that you're having ln, concentration of H2O2 after some time, minus ln, the initial concentration of H2O2, being equivalent to minus Kt. Then lastly, we need to also write the units of what? K. So in first order, the units of K, so let me say K units, are equivalent to what? S to the minus 1, which is the same as 1 writing 1, S to the minus 1. Now for the second question, you're having the reciprocal of what? The concentration of the reactant. So you're having C4H8, which would be, I think, but4N. Yeah, but4N. So here, to determine the order, remember the reciprocal versus time, the reciprocal of the reactant versus time will always give you a second order. Then the corresponding rate law will be 1 over the concentration that you have, which is C4H8, minus 1 over the same concentration you have now at the initial point, which is C4H8 naught. And this is equal to what? KT. So reciprocal of the concentration of C4H8 after some time minus the reciprocal of C4H8 at the initial start of the reaction. Then C is saying find the units. So the K units are equivalent to, since this is second order, this will be terminal CL1, this will be M. Remember, this will be minus 1 times S to the minus what? 1. So this is simply the second order. Then looking at 3, you're having ln pressure of CH3 and what? C. So when it comes to the order of this reaction, be mindful that since we're having ln, it's going to be what? The first order. So in simplicity, when it comes to the corresponding rate law, this is going to be ln concentration of P CH3 NC after some time minus ln P CH3 NC at the start of the reaction being equal to negative what? KT. So the ln of the concentration of PCH3NC after some time minus the ln of PCH3NC at the initial start of the reaction. Then the units, since it's the first order, the K units will simply be equivalent to S to the minus 1. Then looking at the last one, it says that you have the concentration versus time. It's literally the concentration versus time. So for this one, it's quite simple because this was showing us the 0 atom order. Then to show the corresponding rate law, this is just going to be the concentration of what you have, which is ethanol after some time minus the initial concentration of what? Ethanol being equal to negative what? KT. Then lastly, the K units. So the K units for a 0 order is just going to be M by S to the minus 1. As simple as that. Alright, so now these are the questions that you'll come across where you have graphs. Let's look at a different type of problem. Now, in type 2, you can have calculations involving integrated rate laws. So now integrated rate laws can be used to solve for a variety of variables such as reaction time, initial concentration, concentration remaining after a particular amount of time passes, and the rate constant, which we all know is K. So now the only way you can solve this is by first scanning the problem that you have been given. Whenever you scan the problem for the stated reaction order, you then have to select the appropriate integrated equation that is found on the table, the summary table that I gave you, which is the AP equation sheet. Then watch for units of time. They might be hidden in a table heading or in the units of what? K. Because sometimes the order might be in the units of what? K. They might give you the units, and those units will represent the order of that particular reaction. So don't forget about that. Okay, so let's look at some questions. So say they're saying, what is the value of the rate constant K for a second order reaction if the reactant concentration drops from 0.65 to 0.0981 morality in 17.0 seconds. Include appropriate what? Units. So we've already been taught that it's what? A second order reaction. So we know the formula is simply 1 over the concentration of the reactant after some time minus 1 over the concentration of the reactant at the initial, being equal to what? KT. So all we have to do is to collect data. Ask ourselves, what is the concentration after some time? Now they're saying, what is the value of K? If the reactant concentration drops from 0.657 to 0.0981, so it's like the final concentration, which is the concentration after some time, which is equivalent to 0.0981. Then you need to also find the initial concentration. So it dropped from 0.657, so that was the initial concentration, 0.657. Then you also have to know the time. So the time is what? 17 seconds. So all we have to do now is substitute what we have in the formula. So it's going to be 1 over the concentration, which is 0.0981 minus 1 over 0.657 being equal to K times what? 17. Now if you manipulate this clearly, what you'll be having is this. If you divide both sides by 17, even this side 17, you have your K value being equal to 1 over 0.0981 minus 1 over 0.657. The whole of this will be over what? 17. If you compute this on the calculator, the right constant K will be equivalent to 0.5101 morality per what? Second, like that. And this will be what? Our answer. It's morality per second because it's in second, or it's in what's a second order. So which means that you have, in fact, supposed to be m to the minus 1 times s to the minus what? 1. And these are the correct what? Units. Now let's look at a different question. It's saying that you have a reaction that is showing the decomposition of hydrogen peroxide to water and oxygen. Now it follows the first order kinetics with the right constant given in minutes. Calculate the concentration after some time, which is 10 minutes, of hydrogen peroxide if the initial concentration is 0.2 moralities. So what we'll do is quite simple. Since I said this first order, this will be ln concentration of what? H2O2 minus ln concentration of what? H2O2 at the initial is equal to what? Negative KT. Then we can collect data. So let's look at the final concentration. What will be the final concentration? So the final concentration is actually what we're looking for, but the initial concentration we know is 0.2. Because you have been asked to calculate the concentration after some time, which is 10 minutes, if the initial is 0.2. So you have the initial concentration, and the time is simply just 10 minutes, and the rate constant, I guess, has been given to be 0.0410. So since the rate constant is in minutes, and the time is in minutes, there's no need of converting time to seconds. But if you want, you can convert time to seconds, but the moment you convert the time to seconds, also convert the minutes on the rate constant to seconds, then you can plug in. So this will be ln concentration of H2O2 minus ln concentration of O 0.200. I'm going to put the initial part, let me just put it in brackets, 0.200 being equal to negative 0.0410, then times the time, which is 10. So if you begin to forward this out, you end up having this concentration of H2O2 to be equal to, you say in of H2 O2 is equal to minus 0.0410 times 10 plus ln of 0.2. And if you compute this, you have the concentration of H2 O2 to be equal to 0.132 moralities. Let's look at the last example. The rate constant for a second order reaction is given. If the initial concentration is 0.2, how long will it take for the concentration to increase to that? So we're looking for the time now. So we know that it's a second order, so it's going to be 1 over the concentration after some time minus 1 over the initial concentration should be equal to what? Kt. So if you collect data, look for the concentration after some time, and in this case it's 0.113. Then look for the initial concentration. The initial concentration is simply 0.26. Then the rate constant K is given to be what? 0.13. And the time is what we're looking for. So if we want here, you can just make T the subject of the formula. Then you have K being equal to 1 over concentration to some time minus 1 over initial concentration over what? Over K. Sorry, it's supposed to be K. So let me put this K and T. So over K. Then you have T here. So it will be T being equal to 1 over the concentration, which is 0.13, minus 1 over 0.26 over 0.13. And if you compute this carefully, you have the time to be 13 seconds. Alright, so this is just a quick recap on integrated rate laws and kinetics. This is Mr. Hussein Mosapi. Don't forget to like and subscribe to the channel. And remember to strategize before you become a statistic. And try and push for that A+.